Supercritical fluid extraction is simply extraction which is performed with a supercritical fluid. In this case, carbon dioxide. Because the system uses carbon dioxide and a small amount of co-solvent, 3 to 5% co-solvent, this is considered a green technology because carbon dioxide is non-toxic, non-flammable, and non-explosive. This is a supercritical fluid extraction system that can be used to extract compounds of interest from a more complex matrix. For example, vanillin from vanilla beans or caffeine from coffee beans. In addition to being an extraction system, the system can also be used to prepare micron-sized particles, powders. This is particularly useful for preparing powders of thermally labile drugs. The particles can be micron-sized particles which can be easily inhaled, so it makes for a good drug delivery system. By manipulating the pressure, temperature, and concentration of the particles, of the material to be made into particles, you can control the average particle size distribution of the powder. The system is called an SFE 500 MR. SFE simply stands for supercritical fluid extraction. 500 because the extraction vessel and the collection vessel are both 500 ml in volume. M stands for multiple vessels. The R stands for RESS, rapid expansion of supercritical solvents. That's where the particles are formed. Compared to other commercially available supercritical fluid extraction systems, this one has some unique features. First, it is completely automated in its operation. The competing SFE equipment is operated in a manual mode. Compared to traditional sock slit extraction, SFE offers the use of environmentally friendly CO2, so it's a green technology compared to solvent extraction with a sock slit. Much lower operating costs because you're using much smaller amounts of solvent and thus lower solvent costs as well as lower solvent disposal costs. Much lower extraction temperatures are also used in this system. The critical temperature for carbon dioxide is 31 degrees centigrade, and so one can perform extractions at very low temperatures. This is important when you're extracting thermally labile compounds from natural products. Components of the extraction system include the recirculating chiller. This provides chilled ethylene glycol solution to the heat exchanger. The heat exchanger cools the CO2 before it goes to the pump. When the CO2 reaches the pump, it is a liquid, allowing the pump to deliver denser CO2, and it cools the pump, reducing pump head cavitation. The chilled CO2 is delivered to the dual-headed CO2 pump that pressurizes the CO2. Its maximum flow capacity is 50 ml/minute of liquid CO2. This high-pressure CO2 can then be mixed with a co-solvent, sometimes called a modifier, and typically that's added in amounts of 3 to 5% from this modifier pump. The modifier can be any organic solvent. The mixed solvents, CO2 and co-solvent, are then sent to a second heat exchanger here, and in this heat exchanger we heat the mixture of CO2 and solvent up above 31 degrees centigrade, so it is above supercritical conditions, and we now have a supercritical fluid. The mixed solvent leaves the second warming heat exchanger and goes into a three-way valve. The three-way valve can direct the flow either to the solvent extraction system or the particle formation system. When we're using it in the extraction mode, the flow is directed toward the bottom of this 500 ml extraction vessel. The CO2 flows in through the bottom of the extraction vessel, flowing up through whatever it is the extraction vessel contains It dissolves some of those components, maybe caffeine from coffee beans, maybe some drugs to be tested from plants, from the plant leaves from the Amazon. The dissolved components and the flowing solvent leave the top of the extraction vessel and go into this back pressure regulator. The pressure is reduced in the back pressure regulator to about 3 bar. Now, it turns out that the solvation power of a supercritical fluid is directly related to its density and thus its pressure. So when we reduce the pressure, things which were dissolved in the dense high pressure CO2 now precipitate out of solution as a solid. They are swept from the back pressure regulator to the collection vessel. In the collection vessel, the precipitated materials which were extracted from the material in the extraction vessel are collected in this fraction collector, along with the small amount of co-solvent that was added. The flowing CO2, which no longer has any solvation powers, is vented from this vent. Some of the things that this system has typically been used for is cleaning components from chemical residues, separation of low molecular weight oligomers from higher molecular weight polymers, isolation of flavors and fragrances, as well as isolation of pharmaceuticals and nutraceuticals from more complex natural product matrices. Now let's move on to the other part of the system. In addition to extraction, the system can also be used to produce micron-sized powders based upon rapid expansion of supercritical solvents, RESS. Previously, powdered pharmaceuticals were made by mechanically grinding. This leads to very large particle size distributions and sometimes results in the formation of pastes due to the heat of grinding. Dissolving the same materials in a supercritical fluid, and in this system, the material that we want to make into a powder is in this chamber at high pressure, and it's in the presence of an organic solvent. It's dissolved in an organic solvent. Dissolving the same materials in a supercritical fluid and rapidly spraying through a nozzle as it is depressurized eliminates the problems of forming pastes and very broad particle size distributions. The system uses the same fluid delivery components as the extraction system. So the chiller, the pumps, the heat exchangers are all the same up to the point of this three-way valve. The three-way valve now is switched not to the extraction system but to the RESS, so that the flow leaves the three-way valve and goes into this valve, which then goes up to this chamber which contains the material that we want to make into particles. The material dissolved from the RESS dissolution chamber is then flowed to this heated nozzle where there is a 4/1000th of an inch orifice. On one side of the orifice there's very high pressure, up to 400 bar. On the other side of the orifice is 1 atmosphere. And so as the supercritical fluid and its material dissolved in it traverse this heated nozzle, the supercritical fluid loses its solvation power, and the things which were dissolved in it at high pressure are precipitated out as tiny particles, micron size, as the system is depressurized. And those particles are collected in this collection tube. The CO2 is merely vented out the back. In general, the applications include preparation of asthma medications, controlled release drugs, and microparticulate coatings.